So, welcome back to the afternoon session, and it's a pleasure to introduce Pietro Ballone from NTNU in Italy to talk about fracture and simulations.
Yes. First of all, thank you very much to the organizers for the invitation. It has been my first time in India, and I've been very, very happy, and I liked it, enjoyed it very much. So as you know, I am not an expert of fracture. To be precise, I am a replacement for Alex Hansen. Most of you know him. He could not come, and he told me, please go. And so I'm here talking about fracture, but usually I do other things, and but excuse me for that. I will try to do my best. So my connection with fracture has been mainly about the problem of creep in polymeric fibers. So it is a kind of simulation theoretical point of view. So I am trying to use simulation methods to clarify some aspects of very idealized statistical mechanics models to see how to include new features or to understand where some features come into the model, so by changing the interaction, changing the conditions, etc. So it's neither an attempt to reproduce a specific material, nor an attempt not to do just simulation. It's a simulation as an auxiliary tool to do statistical mechanics. For this reason, the role of Alex has been extremely important because he's an expert of the statistical mechanics of fracture. Okay, so I organize my talk into those points, so we will give a few motivations and a short introduction. I will talk briefly about creep in fibrous materials, what happens and what do we try to reproduce. I talk again briefly, because it's been mentioned several times, about the fiber abandon model. And fiber abandon model is an extremely important model, but is a kind of easing model for fracture of fibrous materials. But it has many missing features. So there are many things that are not there because of the idealized nature. And piece by piece, we would like to reintroduce those features. Piece by piece, precisely because we want to understand what is the connection of what we introduce to what we get out. And so eventually, the end point of this process is an atomistic simulation. So when we will have a model that includes all the chemistry, all the interactions in a realistic way. And then we will talk about what we plan to do for the future. So it's not a well-defined scientific talk with results, etc. So I'm talking about our line of research on those subjects. So I'm drifting in between a few things. Okay, a very, very quick introduction, because this is not really needed at this conference. The audience knows about fracture much more than what I do. But essentially, fracture has been a basic problem since the beginning of civilization. So people needed to know when things could resist to load, to external solicitations, etc. And so for this reason is of great practical importance, but is also of great conceptual importance. It is in fact at the same time, part of the everyday experience, but essentially difficult because it is multi-scale, it's non-linear, non-equilibrium, etc. Okay, and so for that reason, we are interested in it, and for that reason, so there is still a lot to do. And so, I think that so is a good subject to address. Okay, so essentially the framework, so what is the general picture? So again, things that we have already seen a few times, and I only mention quickly. So the general framework is that of tensile strength of materials. So when a material resists, what does it do when it resists, when it fails, and what does it do when it fails? And how do we know, what do we measure to characterize this behavior? So this is a typical testing apparatus where you stretch something and you plot the stress versus the strain. So you impose a strain and you measure the stress. So when I was a boy, 16, 17 years old, I was trained to use this machine, and we had a large machine applying 50 tons to break samples of metal. So that, so the result for a ductile material like a metal, not every metal, but many metals, is of this kind. So you apply a moderate strain, you get a linear stress, so Hooke's law, so the slope is the Young modulus. And then you start to have plasticity and to have to have a variety of features that are much more complicated, less reproducible, and that are the focus of what we want to discuss. Essentially, we have an ultimate strength. So below that, essentially, the material doesn't break because whatever stress you apply below it, you get a finite strain. Beyond that, instead, the sample will break essentially at once, immediately. So it's a kind of mechanical instability. And so this is fine. This is a first idea that an engineer has of the fracture of the tensile strength and the fracture of material. But it is a static point of view. So it's only the beginning of the story. In fact, so we are now interested in something, so in a time-dependent view of the strength of material. And then in that way, we get into different phenomena, so like creep, fatigue, etc. And so my point, so what I'm discussing is, in fact, creep. In fact, I think that I'm missing something, but no. What we are interested now in is creep. So we are so we assume that this is our starting point. We apply a load below the breaking load, and we are convinced that nothing will happen. We go home and we let our sample under tension. And instead, the situation is not so static. So if you wait long enough, eventually, without noticing it, slowly, your sample will change. So you keep the load slowly over, macroscopic time scales. You will notice that the sample is changing shape and dimensions. And so this is the typical behavior of a ductile material. So eventually it will fail by creep. So not because it became mechanically unstable, but because essentially a system under stress is intrinsically unstable, as we have been reminded 2 days ago. Okay? So eventually, there is so much, in fact, divergent free energy in moving this piece away that eventually we have to go there, at least by thermal fluctuation. So if a system has a finite temperature, it has to break, no matter what. And so what happens at the microscopic level is anticipated. We will see it in detail, but it is anticipated in those snapshots. So we have, in our case, a polymeric glassy material. Eventually, some of the chains that give resistance to the material fail, and eventually the sample will break. Okay, so a few more comments on creep. So creep, as we have seen it, is a slow, irreversible change in the system state. So it is intrinsically a non-equilibrium process, and so to understand it, eventually we will need to put it into, the general framework of non-equilibrium statistical mechanics. So it is intrinsically non-equilibrium because, you see, first of all, it is a quasi-static process. So step by step, we can think in terms, if you like, of a free energy. But the free energy as a function of an essential coordinate, that is the length of the sample, is not bounded from below. So you can go down, down, down without any limit. And so you might be prevented by local barriers, but just wait long enough for rise a little bit the temperature, and so you will end up into two separate pieces. So creep, so in this exception, that is the slow process of just keeping a load and observing what happens, typically goes through different stages. So there is a primary stage where the strain increases, but with a curvature that gives apparent indication of a hardening of the material with time. So it is increasingly more difficult to elongate and perhaps to break bonds. So this is a first stage. And then there is a essentially linear regime leading to a catastrophic failing of the material. So in the primary, essentially the first damages of the structure essentially have the effect of removing the weak bonds, the weak links in the system, and so the system becomes suddenly more resilient. Then in the secondary regime, essentially you see the steady state evolution under thermal fluctuations of the state of the system until when the number of intact links, of intact bonds, is too low to resist the external load. So this is a creepy object that came out of my, so some, I don't know, it appeared at some point in my, okay, so that is creep, that is not only in polymers. So similar behavior can be seen in metals, and it is extremely important in technology, especially for high temperature applications in jet engines or things like that. So what I'm talking about is a specific manifestation of creep, that is the creep in polymer fibers. Okay, so obviously, so polymer fibers are a soft material with, so in which temperature is playing an important role, and so I'm looking at the bundles of polymeric fibers that fail under a tensile load over long times. Okay, so we are not making it just stretching under a large force. We are far below the limiting force for breaking the sample at once. We are looking at the process of thermal fluctuations that break bonds and chains. And so in this way, so what we are looking at is a creep, but is also fatigue, that is a frequency-dependent manifestation of similar phenomena. And of course, viscoelasticity enters, the viscoelasticity of polymers enters into the behavior of the system, and we will need to discuss also that. For us, essentially, theoretical physicists, The interest is in the irreversibility of the process, so the non-equilibrium statistical mechanics can be expressed in terms of entropy generation. We are interested in the heat generation of the process. We want to understand the work hardening, plasticity, etc. So I am a computational person, so my point of view is mainly computational. So many people here in this audience do precisely the things that I do with the slight variations. And so what distinguishes us is the way we analyze and interpret the trajectories. Okay, so that is what. From this point of view, Alex is essential because so he is a good statistical mechanician. Okay, so creep is important in Norway. There's been a long history of applications of creep. So Odin is the main god in the Nordic, pantheon, and he has been hanging for 9 days from a tree to acquire wisdom. And he didn't acquire much wisdom, in fact, but a lot of knowledge. But eventually, after 9 days, the rope broke and he was free. And so that apparently was a manifestation of creep and an early experiment on creep. And so, also, I mean, I came to this subject also for a kind of personal motivation, but personal but shared by most of the people in my generation. So we have seen the explosion of computer power. So I personally went from the IBM 360 in 1978, 1979, to the latest generation of massive computers. This one is at COA in second grade. This is Curie that we use through PACE. And so that has been an incredible revolution. So we have seen things that we could not even dream becoming feasible. So, so we know that the exascale range is within reach. So it's expected to, we are expected to have exascale machines next year. So, 2018 is the time from the exascale. And so, not only we have seen this huge increase of power, but also in amazing development of methods. And we have seen things that we did not believe were computable to be computed. So we know how to compute, electronic structural computation of large systems, proteins. So we can do ab initio simulation of many things. But we have not seen much about things like mechanical nonlinear properties of materials. So this is a field that is intrinsically difficult, and the computational scientists, not all of them, of course, but the majority of them, tried to avoid the trouble of getting into it. And so only now we are trying to, when many other things have been done, we are trying to go into this direction. And this, in my opinion, is a very good subject. So it's not only a matter of power, of computer power, it's not only a matter of simulation, but it's a matter of interpretation of the results of the simulation. So being able to establish connections between what we compute and what we measure. There cannot be a direct comparison. So we cannot pretend to compute 10 to the 10 or 10 to the 15 atoms. But we have to establish protocols to translate the simulation results into the quantities that we measure. So creep in polymeric materials had a long history, essentially starting from beginning of 20th century, that is 1900 something, with a peak of activity in the 50s perhaps. It has generated many interesting models that, however, so I consider from my point of view of historical interest. Of course, there is still activity and things can come out from that. But from my point of view, the step 0 is the fiber abandon model, okay? So this has been introduced by a few of you, including yesterday, and so you know what it is, perhaps not all of you, so I shortly remind what it is. We consider a system, confined by two rigid plates, and attached to those plates, so those plates are joined by springs. The simplest realization of the model, the springs are all the same, so they have the same spring constant. So a force that is linear in the, in the stretching up to a given point, to a given deformation, at what point the resistance just disappears. The spring fails, and so the load that it was carrying is redistributed on the other springs. So this is a basic model, and what distinguishes the different models is the rule you assign to the redistribution of load once a fiber has broken. So each fiber has a different, slightly different value for the maximum distance that can be stretched or maximum load that it can carry. And this distance is a random variable. And so essentially you pick from a distribution the value of the maximum distance or tension that you can apply to a single chain. So in the simplest case, there is no chain interaction. The interaction is only through the plates. So once you break one, you redistribute through the plate the load on the others, and this gives a many-body behavior to the system. So this is the origin of the many-body behavior, that however is fairly simple. So we know that it is a mean-field model. Still, I mean, the model that has been formally introduced in this paper in 1945 is the basic model. So we call it the Ising model of fibrous materials, but is applied also to other systems like electric networks and many other. So when the rule to redistribute the load is the simplest one, and we talk about equal global fiber abandon model, in fact, equal global sharing fiber abandon model. The solution, the properties we obtain from solving the investigating the many-body properties belong to the mean-field class of models. And so the fiber abandon model has played an extremely important role because essentially it connects the creep, for instance, to phase transitions and critical phenomena. And so within the fiber abandon model, you discuss about universality, scalar relations, critical points, etc. In fact, so there is, Alex even wrote an entire book on it, the book that I have with me, so if you want to see it. And so it is, despite appearing so simple, it has an extremely rich, variety of properties and phenomena, but still, obviously, it has some limitations. It's extremely idealized. No? So a polymer is not just a collection of chains non-interacting with each other and all the same, etc. No? So there are obvious limitations that are, for instance, there is no real time with the fiber abandon model. We discussed it yesterday. No? Essentially, it's a stochastic process. It's a kinetic model. From time to time, there is an event, and you do not put those events in essentially in a time sequence. There is no temperature, essentially. Fluctuations do not play any role. So fibers are intact or are broken. And there is no, and there is a precise geometric limit. So fluctuations are very limited. Since chains do not interact but through a global coordinate, that is the position of the plates, there is no notion of proximity or distance among chains. No? So two chains, so then we imagine those chains like in this picture. So, but in fact, so if this is Z, if the axis is Z, X and Y don't exist essentially. So then there is no proximity or distance among chains. So of course, some of those things can be reintroduced, but I mean, in the natural most obvious manifestation is that. So there is no cohesion because chain do not interact with each other. There is no point in talking about the pressure of the system. Okay, so chains, of course, might have some idea, you can associate some idea on pressure. So obviously, since there is no interaction, there are no different phases. You cannot talk about coexistence of phases. You cannot talk about surfaces of your sample, nothing of nothing. So although it has been extremely important from the conceptual point of view, it is also very limited. And so, okay, now, fine, we are still statistical mechanicians. We do not know much about dirty things, chemistry, labs, etc. We don't want to know. But still, we want to recover some aspects of reality. And as I told at the beginning, we want to restore them one by one. And so, first step, has been to restore real space and real time relations. So to describe, in fact, an harmonic chain still clamped at the two extremities as before, so it is still essentially a fiber bundle model, but now chains are no longer represented by straight lines, but are represented essentially by particles. So particles and springs, in fact. So instead of straight lines, we have positions, coordinates of beats, and joined at this point by anharmonic springs. Okay? And so those beats have a mass, something that introduces inertia, that introduces a time, so time evolution. Now, about our system, we write down equations of motion. We can introduce bead-to-bead interaction. In fact, we always have bead-to-bead interaction, at least along the chain. And so we put back many aspects, even though the representation of interactions may be still very idealized, so vastly simplified with respect to reality, but we start to have aspects that allow us to use the model to investigate features that before were excluded from the picture. Yeah.
Directions only along one of the strings which are only parallel, or?
No, the parallel essentially is, so there is no degree of freedom but the length. Okay, here instead, the endpoint separation can be compatible with, an entire space of many dimensions in terms of the positions of the particles. Before, the only coordinate was the length of the sample. Now, our coordinates are the positions of all the particles. We have a much wider phase space. And we have the possibility, essentially, of associating to those positions a potential energy surface. So our beads are, massive particles, so we can write down equations of motion, and so everything looks more natural and realistic. So we are going towards chemistry, essentially. No? That is our aim. And so, okay, Just to summarize what are the general aspects of a model. So we have chains. Chains are made of a fixed number of bits. So as a first step, we took chains all of the same number of bits, but this is, of course, is not essential. But each chain ends with, two bits, special bits, and those are constrained to be on the two parallel plates. So the two endpoints are have a fixed z coordinate. Let me call this direction z. They can still move on the x and y. So they are free to move on x and y, but they need to be are glued, are clamped to those two plates. Then there is an harmonic bond with the first regular bead. Okay, so it's something that you will never break. But along the chain, so the chain is defined by a sequence of what we call covalent bonds that are strong bonds, but strong that can be broken. The potential is a Morse potential that has a finite one depth. So when we exceed the energy, the binding energy of the bond, so the bond can be broken, and it can occur because we apply a tension. It can occur simply by thermal fluctuation. So eventually, you wait long enough, every bond will break. So as first step, we do not introduce an explicit interchain interaction. This is because we want to see step by step what we get. In principle, it could even be realistic because our abandon could be a polymer in a solution. This could be a polymer at the theta point where essentially the interaction with the solvent cancels the chain-chain interaction. As our choice, that we remove at some point, but this is simply a choice, there is no, so we could do one way or another, we decided that bonds that break do not recombine. Essentially, our idea is a chemistry idea that essentially when you break a covalent bond, the covalent bond will not stay as a dangling bond. So that is an idealization of the quantum chemist. So you have a broken bond, some dirt, some OH minus, some radical that is in the system will immediately saturate it. And so a broken bond will not recombine. Okay, so once we introduce this, our single chains that before were simply uncooked spaghetti, now are essentially elastic entities, so we can look at end-to-end distance distribution, we can look at the elastic modulus of the system, etc., and we recover the properties that we find on the elementary textbooks. So the end-to-end is the square root of the number of bits times length, etc. And so this one appears to be a polymer. So that of before was just a spring. Now this one has some features of a polymer system. Okay, so I wrote down the Hamiltonian, but I don't think that we want. Sorry. Yeah. By a Morse potential. And yeah, the position, I mean, so those are particles at equilibrium at a given temperature. So they will move at random. So if you take a snapshot, each chain appears like a random walk. No. I don't remember what we did. It doesn't matter. Once you have equilibrated, you lost the memory. So we always shake energically our system at the beginning to make sure that what we do does not depend on the way we prepare it. So in this case, we brought everything to the liquid, into the liquid state, and then we annealed or quenched the system. But yeah, I mean, since it is essentially a chain at equilibrium, you look at it at a given time, and that appears as a random walk. Okay, so essentially, so I do not want to go into the details because we have 10 minutes left, but essentially, so we have the interaction with the particle on the wall with the first bead that is, as I told, harmonic, and all the chains are defined by the Morse potential, that is something with a finite depth, but we cut at a given distance. So the important parameter is the weld depth, that is D0, and the equilibrium bond length. So we use scaled coordinates. So our unit of energy is the temperature, it's K-Boltzmann T, and in our simulations, D naught is of the order of 10. So it's something that is strong, but not so strong that the bond cannot break by fluctuation. Okay, so this is just to show that we can write explicitly our Hamiltonian, and so we compute the forces on the ions, on the beats, and we can carry out a simulation. So simulations are done under two different conditions. So the most important one is, so most of our simulations have been carried out at constant force of the plates, at constant tension. And so plates have no mass in our picture, and simply we adjust the position of the plate instantaneously in such a way that the force, the sum of the forces from the chain to the plate is exactly the value we want. So this is a process exact, so we just at each instant of time in our simulation, the force from the plate to the chains, or equivalently from the chains to the plate, is strictly constant and equal to the value we give. So we talk only about the forces along Z, because, and in terms of global coordinate, because we do not have any pressure in the other dimensions, because chains do not interact with each other. So, I mean, this is simply the description of what I told, that is, we simply compute the force, the force from the chains to each of the plates. So this is an expression, a linear expression in the coordinate of the wall that we can solve in one shot. And we say, okay, so I have all my beats in these positions, where is the wall? The wall has to be at this position. Okay? So it's an automatic procedure. So our experiments are done either in this way, that is fixed tensile load, or we strain at a constant rate. Okay? But most of the simulations have been done in this way. The two pictures are essentially equivalent. It's like looking at a system and in two different statistical mechanical ensembles. Okay, so we carry out Langevin equation simulations. So, because, I mean, we are performing work on the system. And so we want to stay in a well-defined thermodynamic state. We remove the extra heat. When we want to see this effect of heating, we remove the Langevin friction. Okay, so in the Langevin dynamics, we have forces that are the usual forces. We have a friction. So if you tend to heat the system, you just remove energy through this friction. And we set the temperature by the white noise we add to our equation. So there are ways to do it. And so we do not want, we are not interested much in the details. So simply, just to give you an idea, so we have bundles of 400 chains. So, sorry, these are beats, not chains. Each chain has 100 beats. For each condition, that is temperature, load, etc., we probe from 20 to 200 samples, independent, generated in an independent way. Most of the simulations have been done at this temperature in scaled units. And and again, in scaled units, we did something like, I don't know, 15 different loads. And the simulations continues until when the number of chains in the system is reached. So we break all the chains in the system. At that point, we stop our simulation. So we know that we are far below the limiting force, and in fact, breaking occurs by thermal fluctuation. So simulations can be very long. Simply, we have many workstations distributed into the offices, and we put our jobs, I mean, despite our colleagues complain, we put the jobs and they stay there months. So some of the computations lasted 6 months, and so we were doing something else in the meantime. And okay, so this is what happens. No? So essentially, this is a sequence. I have a movie, but it was on the other computer that we are unable to connect. And so progressively, you stretch and you break. So here we display only 1/5 of the particles, so otherwise you don't see anything. And this is what happens. So at a moderate force, simply waiting, we see that the length of the sample fluctuates but increases up to the catastrophic failing of the system. And you see that more or less you can recognize the stages of creep that we discussed at the beginning. So a rise, a nearly linear regime, and then there is a collective behavior of, so you break one, you increase the load on the others, and so the breaking rate accelerates. Okay, at this point is just to show you a couple of slides of results. So we can measure the number of broken chains as a function of time. And so what we had before was the length. So it's one representation of what happens in the system. Yeah. Sorry?
The time, I mean the time on the x-axis.
Yeah.
Just the same time that you do on the loop. How is it different? How is it more visible?
Because the other one, I mean, the event of breaking, so one attempt is breaking one bond. In reality, so you are saying that in the fiber bundle, you could take the one attempt equal unit of time. No, because in fact, one attempt means one breaking of a bond, essentially. And that does not take place in a regular way like in a clock. That is a random variable that you can, in fact, estimate by an Arrhenius, by some Arrhenius plot. But it's not regular. Okay, no, not only, but this is the first step. So interesting point is when you start adding the interaction, and that between chains, and then.
Also, there were attempts in the original fiber bundle mode that if any of the fiber has a force on it,
Yeah.
Above threshold, of course, like
Yeah.
but if it is below threshold, then with the original probability of that gap from its own threshold to the force.
Yeah. Okay. No. I mean. Yeah. So. No. Yeah. No. No. It's not a frequency. It's a fluctuation. Yes, a fluctuation in the behavior, but it's not a frequency. So you can have a frequency if you use the fiber bundle model in a kinetic Monte Carlo sense. So you say, okay, I'm at this point. When will it be the next event? I just draw a random number, and I decide when it will be the other. So in that way, I mean, this is what people looking at the damage in metals by radiation, etc., do. So they have those events that are discrete, separated by long gaps. So because this is what we do, no? So we have events discrete and separated by essentially time, long time where nothing happens. So in that sense, I mean, if that is the condition, you could use the fiber bundle model in kinetic Monte Carlo sense. And then you recover an estimate of time. But otherwise you is arbitrary. You say, okay, I take one step, so one attempt equals one time unit. Well, you know. But I mean, so if we look carefully, there are other aspects. But okay. So in any case, so since the time is almost exhausted, so simply what I want to say is that we have a very detailed view of what happens. So I mean, it would take some discussion, but essentially one aspect we analyzed is the role of the last stage of, an avalanche stage. And to define the avalanche state, we had to identify the normal behavior when the system was just failing by independent fluctuations. So what we notice in the computation is that the bond breaking goes at a constant rate, but the chain breaking, no. It has a more complex behavior that is reminiscent of what you measure in experiments. So bond breaking is a rather rare event. Bond breaking is not the same as chain breaking because you can break more than one bond on each chain. And so the two, at some point, split. We are able, by a kinetic model, to define the normal behavior, that is this line. When what we measure in the computation deviates from that, this is the avalanche. So in this way.
When you break a bond in the chain,
yeah, it does what?
How is the force exerted? How is the tensile force exerted?
Yeah. So if you look. No, there is nothing, simply the inertia of that. Yeah, because there is no interaction with the sign change. No? So in fact, so since we want to finish, otherwise many of you will miss a flight, and so I don't want to be responsible for that. Let us, so just 1 minute to comment on one point. So I told that we made the choice of having no recombination, and I told so that almost doesn't matter. No? Instead, it has a dramatic effect, because if you have a bond recombination, you have a steady rate of bond recombination. If the tension and the temperature are such that the natural rate of breaking bonds by fluctuation is below that, the bundle will not break. So what I told before, that every bundle is unstable, is not true if you have bond recombination, because bond recombination will take place at some rate. If you break bonds at a lower rate, then that is stable. And in fact, we see really a transition point, a kind of critical point between, you see, this is the number of broken chains. At a node, it reaches the size of the system. At a slight, not so much lower node, instead it is constant. And in between, you get whatever length. So you have huge fluctuations. That means it's a kind of almost a critical phenomena. So those are the simulation constant strain rate. But let me just skip to restoring the interchain interactions. So as we have Morse potentials along the chain, we take Morse potential between each bead and every other bead. Simply we take it much lower, in such a way that we still have the chains as a dominant structure. But in this way, essentially, we restore, so details are here. I think that at the end, the slides will be distributed. So now we have packing. We have a natural density of the system, so the periodicity along the x and y directions matters. And so for this reason, we tested, we did simulations with and without periodic boundary conditions along the two directions, the two complementary directions. When we did have periodic boundary conditions, we set the periodicity. We used a Parinello-Raman approach to keep the pressure constant. And so we carried out our simulation. So if you compare, so if you remember what we had at this point, where we had, chain breaking essentially everywhere at random, so without any structure, where any pattern, or where breakings took place, now there is, you immediately notice a difference. That is what has been discussed yesterday. That is, there is a nucleation of a bubble. So we separate the two phases, the particle phase and the vapor. Okay? And since this is a simulation with periodic boundary conditions, it has to take place in somewhere in the system, and it takes place in a localized way, so as a nucleation event. And then it grows until when it breaks. Okay? If we remove periodic boundary conditions, we have necking. And because, so it is much easier so we do not need to wait for a nucleation event. So it immediately starts deforming the surface, and eventually it breaks. Of course, I mean, the two processes are in competition. So if we increase the cross-section, there will be, as we've seen, there will be an equilibrium or a competition of the two processes. Okay? And so this is important. For us, it's essential because we are looking at, we are aiming at nanometric bundles. And so a specific feature of going to nanometric dimensions is the fact that they break in an essentially different way. So we are not saying, so we are looking to it from our point of view, but you know, we have seen it during those days more than once. Okay, so just let me summarize. So I hope that I gave you an idea, simply an idea of what we are trying to do and why. So that is a strange mixture of simulation, so it is something dirty with you know, some attempt to connect to statistical mechanics. So at this point, we are in the process of simulating a fiber bundle model based on interacting particle, and this is an intermediate step between idealized models, and we are going, essentially, next step will be a chemically accurate representation of a system using, you know, standard force fields modified just in such a way that they will break. Right now, most force fields don't break, it's harmonic. And so we will change slightly that, but you know, lamps, etc., already does more. So what we are doing is going from the most idealized to the more refined, adding contributions one by one, because we want to see what comes at each step. So for instance, as an example, so interchain interactions are needed to describe the nucleation stage, how you know, how the breaking starts, nucleates or doesn't nucleate in the system. I mean, there are plenty of features that we didn't have, I didn't have time to discuss, but we see many important, intriguing, you know, phenomena like the effect of packing, in the sense that under some conditions, our samples are partly crystallized, and are partly crystallized essentially because of size and of the size of the particles. And so we have packing, we have elastic properties, we have cohesive effects. So it is much richer than the original bundle. So right now, what we are doing is to talk to biomedical and biology colleagues, because we want to go into biological fibers. And there are plenty of biological fibers from, I don't know, tubulin, collagen, to the microtubule, and so plenty of structures in the cytoskeleton, etc., are fibers. Important fiber, you know, biofibers are amyloid fibers that, you know, are connected to very dramatic diseases, but also, you know, I finish, it's over. So, but are also elements in, so building blocks for nanotechnology. And so we are collaborating with them. We have a project funded by the Research Council to do, you know, bundles of biomolecules. So, okay, I stop here. And,
with spring constant randomly distributed for different nodes. And then if you try to pull, stretch it with certain criteria beyond some, again, some similar to fiber bundle, this will break. Won't you see similar feature?
Yeah, essentially the fiber bundle is quenched disorder. Instead, so in our model, each bond is evolving. Sometimes it's beyond the limit and it doesn't break because geometrically is too close and not. So there are more realistic fluctuations, essentially. So I'm not saying that you cannot introduce fluctuations in the fiber bundle, but there are essentially different fluctuations. At most, they are frozen into the system, in the distribution.
No, but I'm talking about a random network where it's not like one fiber. They're all, it's a network.
Yeah, it can be a network, so we know that we can compute the winding number, and so there are intersections of chains. So there is entanglement, and sometimes we have problems moving one chain across the other. So in the interacting case, so you do not move one chain across the other. And so we can have a knot, we can have, an entanglement, we can have all those things. And so obviously we want to see the effect of those things. Simply it will take some time because there are, an endless number of features. So we are looking also at the partial crystallinity of the sample. So typical polymers are a mixture of amorphous and crystallized. And so the combination of the two is essential. Like, I don't know, spider silk is so special because of this combination of crystalline grains in a matrix, in an amorphous matrix. And so we are looking to that right now. And so, but the other, yes, is the degree of entanglement. For that we need longer chains. But that is one of the things that we want to do. By the way, in this case, we can study chains as long as we like with interactions. Without interactions, curiously, chains are, so bundles are unstable because, one or the other bond will be broken. So if you go to a long chain, it breaks immediately and without you, before you realizing it is broken.
First thing is, in case, so you for the 2D model, you showed the Morse potential between two beads of two chains, right? For the 2D case, where that one chain is interacting with another chain, you have included the Morse potential between the bead of the one chain.
Yeah.
But in principle, you could just have a pure repulsive interaction between instead of a Morse potential.
Absolutely, yes.
But then would the mechanics of the system change?
Well, in principle, if you apply a pressure, that is the same as having a cohesion. Most of the effects are due to the size, not to the cohesion. No? So packing is a crucial aspect. No? So hard spheres crystallize. So it is not a matter of attractive interaction. No?
And just a small comment, still you don't have, so when you are doing looking at chain interactions, the springs are still not interacting in principle. So
what do you mean the springs are not interacting?
So you have beads which are connected by springs, but it's not a full description in the sense that the spring of one chain is not interacting with the spring of another chain.
So the spring is a representation of the chemical bond. No? So that even if you do an ab initio computation, you are in a situation like this one. No? So that the only degree of freedom is the position of the nucleus. So I do not know what is a spring-spring interaction. I do not understand what it is. Is it clear what I mean? We can discuss, if we I don't know whether now there is a break or there is a conclusion. I don't know. Yeah.
So you introduce temperature in your approach. and then you also compute the temperature from the vibrations of your particles that can change, as far as I understand. So
No,
do you couple that back onto the vibration if you have diffusion of temperature in your model?
No, I mean, we are, in most of the computations, we have an Angevin dynamics. That is, we have one parameter that is the target temperature. But of course, we can compute also the kinetic energy. I mean, as a simulator, so we immediately think in terms of the temperature. But obviously, the only temperature that is meaningful is the parameter we put into the Angevin. The rest is just average kinetic energy. So I wouldn't.
There's no thermalization between the
there is thermalization. Absolutely, there is thermalization. But as a statistical mechanician, I do not want to hear that average kinetic energy is temperature.
Okay.
So temperature is the parameter that tells me where heat flows.
But it's homogeneous in your case.
It is homogeneous, yes. But so the system is always, if I'm using the Angevin point of view, temperature is fixed, is that number, so the target temperature, and I have a fluctuating kinetic energy. Okay. So it's only, you know, in some so isolated system, microcanonical ensemble, etc., that temperature turns out to be precisely the average kinetic energy, etc. No? So it is.
Thank you.